All right, class, so let's continue with our examples of exponential functions. Yes, one thing I had forgotten to tell you out here, since we were talking about it, sure enough, we said that the domain is all real numbers, but as you see from these two graphs is that the range of the exponential function, that's going to be important as well, is 0 to infinity. So only positive values come out of it. So domain is all real numbers, yes? Okay. All right, so let's go through some examples, and it says a population numbers $11,000, Jesus, 11,000 organisms initially. So what does that mean, 11,000 organisms initially? That simply means that your initial value, the A that I put in the front, is the 11,000, okay? And grows by 8.5% each year. What does it mean that it grows by 8.5% each year? That the growth rate is 8.5%. So if it wasn't growing, it would stay at 100%. It grows by 8.5%, so that means our base is going to be 108.5%. That translated into a usable number is 1.085. Okay, so from the 100%, again, where nothing is happening, doesn't grow, doesn't decay, this one's going to grow by 8.5% each year. So after 1 year, you will have 100 plus 8.5%. So all you started with plus a little bit more by this much. So sure enough, anytime we want to use a value in calculations to drop the percent symbol, we divide by 100, right? Per means over. Percent means over 100. Okay, write an exponential model for the population. So here it is easily. F of x is equal to 11,000, yes, times 1.085 to the power of x, or call it t for time, whatever you want, yes? And so, and it says use it to find the number of organisms 2 years from the initial time. So I'm assuming that x is years, so then just simply plug in a 2 into this function, put it in your calculator, okay? Put it in your calculator and you will get approximately 12,949 organisms. All right. Okay, let's try this again. The fox population in a certain region has an annual growth rate of 9% per year. So what does that mean one more time? That means R is 9%, okay? And it says in the year 2012, there were 23,900 foxes counted in the area. So what is the fox population predicted to be in year 2020? So we can make this our initial year. So let be year, x be years since 2012. So that means in year 0, you had 23,900 foxes, okay? All right, so that means this is our initial value A. So we can easily make up our function. At 0, at time 0, it starts at 23,900, yes? What is the base? Well, it's growing, yes, by 9%. So our base is going to be 1 plus 0.09, in other words, 1.09, yes? And again, being an exponential function, the x is in the exponent. So what will be the population predicted to be in 2020? 2020 means what? 8 years later? Yes, so all I have to do is plug in an 8 into this function. Put it in again in your calculator, 8 years later, on a base of 109% or 1.09. So you're going to get 47,622 mini foxes. Okay. All right. So, I hope you saw that. It says, a radioactive substance decays exponentially. A scientist begins with 100 milligrams. So begins with 100 milligrams, that means that's your initial value, right? So at time 0, you had 100 milligrams. After 35 hours, we have 50 milligrams of the substance. So 35 hours later, you're left with just half. This is also called the half-life. So something decays, eventually becomes half of what it was. So it took 35 hours for that. So how many milligrams will remain after 54 hours? Okay, so let X be the number of hours. And let's see what we have in this function that we're trying to set up. So f of x is equal to a, which is 100. We're not sure how fast this is growing, yes? So this is what I know so far. I have an exponential function. I'm not sure of the rate of growth or decay, in this case decay. But I at least know a certain point on this problem. So in other words, I know that if you plug in 35, for x, you will get 50 for your answer. So this is what we could do to solve and find the b value. Yes, so that's what we're missing right now. Okay, so to solve this equation for b, all I have to do is divide by 100 first of all. So I get that b to the power of 35 is equal to 1/2. And what else do I do to get rid of the 35 exponent? Well, to get rid of this exponent of 35, all I have to do is take the 35th root of it. So put that in your calculator. What's the 35th root of 0.5 or of 1/2? And you will find out that that value is 0.98. So out of your calculator, okay? All right. So that simply means that my function here, and then I write it in red, is, again, starting at 100, the base is 0.98 to the power of x, yes? So it says now see what happens after 54 hours. So all you have to do is put in your calculator, I'm going to write it here to have room. So 100 times 0.98 to the power of 54, okay? So how much is that? Put it in your calculator and you end up with about 33.6 milligrams. Okay, so I have another bonus question for you. Obviously the base is less than 1, yes? So what is the decay rate? And the decay rate here is a -2%. So in other words, the amount that you are starting with goes down by 2% every hour. So again, by 2% of, again, I mean, the first hour is just 2 milligrams, right? But now you're left with 98 milligrams. So the next hour, it's a 2% left or decay of the 98. So you're not losing 2 whole milligrams, you're losing a little bit less. So it goes down faster, but then it slows down, right? Because it doesn't have as much base to start decaying, right? To leave you, to get your 2% out of, okay? So yes, that's what a percent change is. That's what an exponential function means. Okay, so let's move on to money. Yay, this is a business calculus class, so we need to talk about money. And money is the compound interest formula, which you probably have seen, but I will explain for you one more time what it means. P is called the principal or present value. In other words, what you're starting with in the present, right now. Say you're investing it at an interest rate R, so it kind of looks like that function that we had right before for a period of time T. So time is your X, right, is what's changing, measured in years. So when you talk about compound interest, the time is always measured in years and not month or days. If the money is compounded n times per year, so that's the change from the problem before, meaning what? To have an n number of compounds per year simply means that your money is being compounded so many times per year. What does that mean? So let's say you're starting with, let's say this problem, right? $4,000, right? This investing in a bank account at an interest rate of 7% per year. So this is the interest rate. And this here is your principal, yes? The amount of money you're starting with, right? Find the amount in the bank after 9 years. That means this is your time, yes? If the interest is compounded annually. So what does that mean, the interest is compounded annually? That after every 1 year, we figure out how much money you have earned, and we're adding that on to your principal. And now the new principal that we're starting with is not the 4,000, so it's not just the 4,000 that grows, but the 4,000 plus whatever interest you have already accrued it, right? So let's say $100 after 1 year. So now we reinvest the $4,100, so you start earning interest on your amount of interest, yes? Now, the money is compounded quarterly, that means we do that after 3 months already. So because we already after 3 months figured out how much you've earned, which might be only $25, yes? But the thing is that $25 starts growing sooner, right? So by the end of the year, you actually will have earned more than just $100. If we would have compounded the money annually, you would have earned maybe $103, right? So a little bit more, and so on and so on. So the more number of compounds, the faster your interest start earning interest, okay? So by the way, A is called future value. That's P is present value, right? How much do you have now? A is what you're going to get in the future, right? So it says if interest is compounded annually, how much money will you get? Well, so that means annually 1 time a year. So plug all of this into your formula, 4,000. 1 plus R is 0.07. N is 1 to the power of 1 times T is 9 years, yes? So 1 times 9, okay? All right, put that whole thing in your calculator, and my calculator said you're gonna get $7,353.84, okay? If the money is compounded quarterly, quarterly means how many times per year? Well, that means 4 times per year. So you're gonna have the same formula, but what's going to happen is you're going to, in place of n, put a 4. So 4 times 9, so see more compounds per year. But again, you earn 7% annually. So after 3 months only, after 1 quarter, you're not getting your whole 7%, right? You just get a quarter of that, so a little bit under 2%. But put that in your calculator and you see your money will grow a little bit more. So $7,469.63. Now monthly should get us more. Yet. Monthly means how many times a year? Well, there'll be 12 times a year. So A is going to equal to 4,000. 1 plus 0.07 divided by 12 to the power of 12 times 9. So what you're going to get is 7,496.70. So it's starting to slow down the rate of growth. You get more, but really after 9 years and all that much more trouble, it's really not that much more. However, we don't care. It's our money, and we want it compounded just as much as we can. So we want the money to be compounded at all times, not just every month, not every day, not every hour, not every second, every split of a second of a second of a second. So we want the money to be compounded all the time. All the time is basically infinitely many times a year. Okay. So the question is, how fast is this going to grow? How can I put in infinity for n? Well, I can't put that in the calculator, but we have this expression, which I put it down here, that 1 plus, and it's, I know I copied this table with m's instead of n's, but it really doesn't matter. The question is, what does this expression become if I plug in larger and larger and larger values of it? So I made a table for you. It's also in your textbook. So if I plug in a 10 for this n, well, fine, m, it doesn't matter. I'm going to get to 2.598, 2.593. Then a little bit more, a little bit more. So what do you see about these values that I keep getting? They aren't getting very large. Moreover, some of the numbers start repeating. 2 is still there. 2.7 is still there. 2.71 starts repeating. 2.718 starts repeating. 2.718.2 starts repeating. And I bet you the next one will have 2.71828, and so on and so on. So these digits start repeating. In other words, what you are merging onto is a value. And that value we label by E. And that value is about 2.71828 and something, something, something. So what this E is, it's an irrational number. And I bet you if you look on your calculators, you'll see an E button right there. And you can press on it and it would give you more of the decimals. If you press on it, you had the 0, so it's going to give you e to the 0, which is 1. So make sure you have a 1 on your screen. And then when you press the e to the x, e to the 1 will get you this value right here. So it's an irrational number. So really, just like pi is an irrational number, and you all know that pi is about 3.14. Same thing here. You don't really need to know all the decimals of e, which are infinitely many non-repeating ones, so there's no end to it. But if you just know it's about 2.71 or 2.72 rounded up because of the 8, then you're really good to go. Okay, so E is about 2.72-ish, let's say. So the reason why it's called E is for its founder, which is Leonhard Euler. And, well, when you find a number, you give it your name. So that's the Euler number, okay, for its founder. So I'm going to stop the video right now just to upload, and I'm going to start another one on this subject.